Hello everybody, and welcome to the last lecture of my 545 class. This doesn't mean this is the last lecture of this class that I may upload to YouTube. There's still a few lectures left that I need to do, but for my students who are in 545, this is the final lecture that is fair game for you on the final exam. And the topic, there's not really a reason why it's saved for last. It's just that's the way it happens to be in the way that I organize the class. But this lesson, this topic, we're going to talk about lateral earth pressures again, and in particular how dynamic motions from earthquakes can impact lateral earth pressures. Now, this is an important topic, and it affects civil engineers all over the world and has for thousands of years. We often want to build things way up high on the sides of slopes because that's where the best views are located. But in order to build things, we need level ground. And in order to have level ground, we often have to create vertical or near vertical walls in the slopes so that we can build whatever it is we want to build. And this is one of the reasons why I am showing you this particular picture. This picture is a picture of the Temple of Apollo in Greece, or at least what's left of the Temple of Apollo. In fact, the only thing left of the Temple of Apollo, interestingly, is this little column right there. And the rest is just the space where the temple used to be. Interestingly, earthquakes over the centuries have absolutely demolished and brought the temple down. But I find it interesting that the retaining wall that the Greeks built, the original retaining wall that they built to make space for the temple, is still standing. And it's a beautiful retaining wall. It's a gravity retaining wall where the weight of those stones is what is holding back the soil and the rock behind it. But notice how intricately cut those stones are and how well they fit together, which I think is one of the interesting keys why that wall is still standing. It was never really engineered, at least not engineered to the extent that we would engineer such a wall today. But I still find it marvelous that such a retaining wall, such an historic retaining wall, is still standing. And there's many walls similar to that located around the world. So you'll have to bear with my allergies today. It's springtime and I have allergies. I do not have coronavirus, but I have allergies. So if I cough or sneeze, just bear with me. So anytime we need to design for structures, or anytime we need to design structures to retain soil or slopes, we have to account for what are called lateral earth pressures. Engineers are really good at dealing with vertical stresses. We're taught to deal with vertical stresses from our earliest civil engineering classes, but that's because gravity acts in a downward direction, and so everything has a vertical stress associated with it because everything has weight. But lateral earth pressures are a little more challenging. In other words, how does that vertical stress translate or cause horizontal stress in the soil? And it's that horizontal stress that we need to hold up when we build a retainment system. So earthquakes can apply horizontal ground motion. So in addition to the static lateral earth pressures that are already there from the self-weight of the soil, the earthquake can add an additional dynamic force to that we may need to account for. So because of that dynamic force, we can have a temporary increase in the loads that our walls are feeling, as well as a temporary decrease in the shear resistance in the soil. And so we may want to account for that. So half my lesson today is just a basic review of static lateral earth pressures, because it'll be necessary for us to understand the dynamic portions that we're going to talk about towards the end of the lesson. So here's a review. When I talk about vertical stresses in the soil, this is what I'm talking about. I have a vertical stress in the soil, and it's the unit weight of the soil times the thickness or the depth of the soil. And that the unit weight times the depth gives me a pressure, and that is the vertical pressure. It doesn't necessarily need to be the effective pressure in this case, but if I'm computing lateral earth pressures, then I want to deal with effective stresses. For more information on effective stresses, go on my office hours page to my CEEN 341 class, my introductory soil mechanics class, and look for the lesson on effective stress, and that will help you out. So to convert a vertical stress, whether it's total or effective stress, to a horizontal stress, all I have to do is multiply the vertical stress by some K coefficient. And the K coefficient that I use is what determines which type of horizontal stress I'm dealing with. And what do I mean by different types? Well, it depends. Because shown here are three scenarios. All three have something in common. They have a retaining wall, and then they have a soil backfill. So you see that in every single case. But in the case on the left right here, the wall is being supported and it's perfectly vertical. The wall has not tilted in either direction, and it's being sustained in its vertical state. In this middle drawing, the wall has been allowed to tilt outward away from the slope as much as it needs to develop a failure plane behind the wall. And that's actually a good thing, because what that means is the development of that failure plane means that this soil that I'm coloring in red right here is the soil that is now being held by the retaining wall, and the rest of this soil over here is holding itself up. So the wall isn't holding that up anymore. So it just reduced the pressure that our wall was feeling. In this third case on the right, the wall is tilting into the soil. So something is pushing the wall into the soil, and it's pushing it with enough force that eventually we develop this shear plane in the soil behind the wall, and the wall begins to push this triangular wedge up and along that shear plane. So you can see that what defines the difference between each of these three cases is what my wall is doing. Is it staying still and perfectly vertical? Is it allowed to tilt away from the soil, or is something pushing it and driving it into the soil? Each of these three cases represents the different cases of lateral earth pressure. For the case on the left, it's what we call the at-rest case. And in this instance, we're going to use a K called K0. That means the at-rest earth pressure coefficient. This case in the middle is what we call the active condition, and we're going to use a K sub A to represent the active case. And this case on the right is what we call the passive case, and we're going to use a K sub P to represent that case. So each of these cases has its own at-rest earth pressure coefficient, which will give us drastically different stresses, but we want to make sure that we line up the right case with what we're trying to model. So what's the difference in those stresses? What's the difference in those earth pressures, sigma H? So sigma H is shown here on the y-axis, and on the x-axis we have the wall tilt. Right in the middle is zero tilt, right there, okay? But if I tilt the wall into the soil, inward, then I'm going to start developing passive pressures. Eventually it tops out, and once I top out, right up here where it levels out, that is my passive case. That's where I've developed the failure plane behind the wall, and my wall is now pushing the soil up along that failure plane. If I tilt my wall outward away from the soil, the pressure against my wall decreases until it eventually levels out. And where it levels out is where the failure plane behind the wall has developed, and now my wall is only holding that little triangular wedge of soil. The rest of the soil behind the wall is holding itself up. So this shows why this is important, because look at this range. Look at this range of horizontal stresses, right? It's a big range, and so you want to make sure that we're assigning the right case to whatever case we're trying to support. So a couple of examples, for instance. What if I have the case of a basement wall and the soil against the basement wall? So ask yourself the question, is the basement wall staying perfectly vertical? Is it tilting outward away from the soil, or is it tilting inward, being pushed into the soil? The correct answer for the case of a basement wall is the wall is being maintained in a vertical orientation. It's neither being allowed to tilt away from the soil or being pushed into the soil. Thus, it would be the at-rest pressure. What about the case of a retaining wall supporting a soil slope? In that case, the wall, like a cantilever retaining wall or some mechanically stabilized earth wall, that wall will be flexible and be allowed to tilt outward. So if it's going to tilt outward, it's going to reduce the pressure that the wall has to be designed for. So in that case, that would be an active pressure. What about the case where, say, I have something that, like an anchor in the soil, and the soil is providing the resistance so that that anchor doesn't move. So this might be a boat anchor, or this might be, say, supports for a building or something that's tipping over, and those supports extend down into the soil, and I'm relying on the soil, the resistance in the soil, to keep that building or that structure from tipping over. In that instance, those supports are transmitting the force down to the soil, and they're pushing the soil, and the soil is resisting, its shear strength is resisting that. So because something is pushing the soil, that would be a case of passive pressures. So hopefully that's a little more clear to you. So a couple of rules that we see from this figure. The active condition has less pressure on the wall than the at-rest condition, but the at-rest condition has less pressure on the wall than the passive condition. The second rule is we can see that it requires more displacement of our wall to develop the passive case than it does to develop the active case. And this really just relates to the fact that soil is strong in compression, but soil, which is a series of independent elements that are just pressing against one another, that system is weak in tension. So that's why we have these different cases. Or it requires more displacement to develop the passive case, i.e. compression, than it does the active case, i.e. tension in the soil. Now the third rule, or the third observation we can make, is that both of these cases, the passive and the active, they level out. And because they level out, that means they represent failure conditions in the soil. Now, we often have a negative connotation with failure, but in this instance, there really is no negativity. It just is. It means that our wall, the movement of the wall, has caused a shear plane to develop in the soil. And so maybe a better way to say this would be both Ka and Kp represent the development of shear planes in the soil, fully mobilized shear planes. So how do we compute these different K values? let's focus on the active and the passive in this lecture. If you want more guidance on the at-rest, you can go find my lecture on lateral earth pressures in the 341 class I have, and then I also have a lecture on lateral earth pressures in my 641 class, my advanced soil mechanics class. Okay, so here's a couple of the popular methods for computing the active earth pressure coefficient and the passive earth pressure coefficient. Probably the most popular and widely used method throughout the world, because it's easy, is the Rankine theory. Another one that's popular and used quite heavily is the Coulomb theory. And then one that I really like but is used less common because it's less conservative is the log spiral theory. It's also more difficult to perform. So we're just going to focus on Rankine and Coulomb in this class because, again, this isn't a soil mechanics class, so I'm not going to talk about the log spiral method. Let's look at the fundamental assumptions that we make with the Rankine theory. First of all, the Rankine theory assumes that all the behavior is described adequately by more circles in the more Coulomb failure envelope. That's this equation, tau equals C plus sigma times the tangent of the friction angle of the soil. Okay, so all behavior is described by that equation. Now, in that instance, the Rankine theory completely ignores friction between the retaining wall and the soil, which is probably the most critical assumption of the Rankine theory, or at least where it's the most wrong. Because there's a lot of friction between the wall and the soil. It also assumes a linear failure surface or shear surface in the soil, which we also know is not true. So those are the two big assumptions that we make that aren't really accurate. But if we just run with them and we go, then we can develop these equations right here. So for the active lateral earth pressure, effective lateral earth pressure against my wall at any depth, it's going to be equal to this equation right here, where this component comes from friction and this component right there comes from cohesion in the soil. If I have a cohesionless soil, then that part of the equation just goes away because cohesion is equal to 0. Okay, simple stuff. And the way that I get my active earth pressure coefficient is using this equation right here. Now, this is a little, you may have been taught this in your elementary soil mechanics class, that it's equal to tangent of 45 degrees minus the friction angle divided by 2. And that's true if you have flat, level ground. But the problem is we're dealing with slopes. We don't have flat, level ground. So researchers and mathematicians have derived a different computation when you have sloped ground. And this is the computation that we use when we have sloped ground. And beta is the slope of the soil behind the wall. So if I have a retaining wall and I have sloping soil, then that angle behind the retaining wall is beta. Okay? Makes sense? Perfect. Yep. And then if I want the equivalent force acting on my wall, this is force per unit width of wall. I'm going to use this equation right here. And the location of that equivalent force is 1/3 up the height of the wall. So from the base of the wall, go up 1/3, and that's the centroid, or that's the location where this equivalent force is acting on your wall. That's the active case. For the passive case, very similar equations. We just have a change in the sign is all. Some change in the signs down here for our passive case, and again a very similar equation right down here. Oh my word. that's not right. I'm missing a K sub P right there. I'm not sure why that's not showing up. There's supposed to be a K sub P in that equation. 1/2 Kp times sigma prime P times H. Okay? Is that right? No. No, I'm sorry. Yep, these are right because the Kp was already taken into account right there in the active calculation. So, forgive me, folks, this equation is correct. There is no Ka in there because the Ka is up here, and down here, the Kp is in that equation right there, so this is all we need. Okay, perfect. Now, let's talk about Coulomb theory. The difference between Coulomb was actually developed before Rankine method was. And it was developed in France by a brilliant engineer by the name of Coulomb. And he solved the problem by just drawing a Freebody diagram. That's right, the things that you learned in mechanics of materials and statics, they really do have application in the real world. He drew a Freebody diagram of this soil wedge that is being retained by our retaining wall. And with all the forces that he drew on it, he then summed the forces so that they would equal 0, and he solved for them. So what he's really trying to solve for is this resulting force acting on the retaining wall, P sub A. The assumptions that Coulomb made was that there was friction between the retaining wall and the soil. And that friction is quantified using this friction angle, delta. And delta has an orientation. If I take this line normal to the retaining wall face, delta is the angle to the normal line to the retaining wall. Okay, so that's what it represents. Then we also are assuming a linear failure surface. And one of the nice things about Coulomb theory is that we can solve complex geometries if we just draw up our Freebody diagram and then solve it with force polygons like we're doing down here. So we can solve some pretty complicated cases actually. Now the orientation is a little different here. Okay, notice that we have to assume an angle of failure. We don't know that right off the bat, so we're going to assume it, and we're going to call that angle alpha sub A for active. And then of course the slope of the backfill is equal to beta. Now here's the equation to get our active earth pressure coefficient. You're going to see that this equation is a little more complicated than the Rankine, and probably one of the largest reasons why fewer people want to use it. Friction angle right there. Now this theta, this is the angle of the retaining wall. Let me go back. Do you see how this retaining wall is sloped? It's not perfectly vertical. That theta is the angle of that slope of the retaining wall. So if it's a perfectly vertical wall, then theta equals 0. If there's any sort of back slope to it, then theta has a value to it. Delta, friction angle between the wall and the soil, and beta, friction, or that's the angle of the back slope behind the soil. And if we had some really smart people in the past who used calculus to optimize the Coulomb equation, and they found using calculus and optimization that we could identify the critical angle. In other words, the angle of the failure slope that always gives us the lowest resistance in the soil and the highest load on the on the retaining wall, and that's equal to this equation right here, where C1 and C2 are given with these equations down here. Now, if I want to solve for the active force acting on my wall, here's the equation right here. And this is why I was confused on the earlier slide, folks. You see how this K is in here? Well, the reason the K is in there is because this is the effective vertical stress. This has not already been converted over to a horizontal stress. So that's why we have the K in this equation. And again, it's going to act 1/3 the way up the wall. So at the base of the wall, go up 1/3, and that's where this equivalent force acts. For the passive case, it's a similar deal. Same assumption, same everything, but this time the wall is being driven into the soil. And I taught you in 341 that applying the passive case of Coulomb is a bad idea. It's a really bad idea. The active case for Coulomb works great, but the passive case doesn't. And the reason for that is in the passive condition, the soil develops a failure plane that looks like this. This linear assumption does not hold very well. And so, and then when I account for the friction between the wall and the soil, in addition to that linear assumption, I often over predict my available passive force on my wall. And remember, often we want to rely on that force to hold something in place. So if I over predict it, I'm actually unconservative. So it can be dangerous. And so this is why I generally say stay away from the Coulomb passive condition. But with that being said, there may be cases where we do want to apply it, if for nothing else, in theory only. So here's the equations for the passive at rest, the passive lateral earth pressure coefficient. Notice that it's very similar to the active, but we have a minus sign right here that I've highlighted with this arrow. So just pay attention to that. And here's the critical angle solved by optimization in calculus. And here's the equation for solving the equivalent force per unit width of the wall. And again, it acts 1/3 up from the base of our wall. Now, that's our review of static lateral earth pressures. Let's get into the dynamic stuff. Now, all of our understanding of dynamic lateral earth pressures from earthquakes began from some really groundbreaking and pioneering work by researchers in Japan. The most famous is one that's commonly used in engineering practice. It's called Mononabe-Okabe. It was published in 1926, folks. I mean, this is before the stock market crash in 1921. This is before the Great Depression. So I mean, you know it's good work if it's still been hanging around for this long and still being used today. There's a less cited paper, but just as significant, published 3 years later by Mononabe and Matsuo. But the findings from the Mononabe and Matsuo paper are kind of lumped together with Mononabe and Okabe today. So we've become kind of lazy and just say Mononabe-Okabe, but really it comes from these two papers. Now what Mononabe did with his students was he developed a very ingenious shake table. Now bear in mind, again, this is the 1920s. This is a sketch from their paper showing how their shake table worked. So here's the cross section. The shake table is held up by two sides of a box that have hinges. And so the sides can actually move, and they have some pressure gauges on the top. So they can measure the pressure that the soil is imparting on those walls. Okay. And then That is attached to this conical shaped eccentric disc. And notice that they have this conical drum where they wrap this cord beginning with the skinny part up here, and as it moves in the direction towards the fatter part of the cone, this rope just wraps around it. And then that's attached to this 30 horsepower motor that just turns and spins. So what ends up happening is when the rope is being pulled at the fatter portions of this conical drum, it causes this table to shake back and forth at a slower frequency. But as we get closer and closer to the narrower portion of the drum, this table would start to shake back and forth much more rapidly. So interestingly, they also accounted for different frequencies in their shaking. I still just marvel and get excited at the ingenuity of these early researchers. It's really, really exciting to me that they were able to come up with this, and that they would measure pressure gauges, or that they measured the soil forces from these pressure gauges. So from these shake table tests that were performed behind this trapdoor system, they developed a theory. And going back to Coulomb's work, where they have their Freebody Diagram, everything's the same with the exception of these terms right here. These are dynamic terms that Mononabe and his students added, where they have a horizontal term that represents the dynamic force in a horizontal direction, and then they have a vertical dynamic component as well. Other than that, everything's the same, but you'll notice some changes. We have a P sub AE, and instead of just PA for the active pressure, active force acting on our wall, this E also means eccentric. So it's the dynamic component coming from the earthquake. And then it's also going to affect the critical angle. So we're going to have a different angle instead of what we might have in the static case. And we're assuming that we have granular backfill here, so cohesionless backfill. And they still assumed that this PAE acts 1/3 up from the base of the wall. Okay? So here are the equations from Mononabe and Okabe and Mononabe and Matsuo. There, you can see that we have a vertical K in here. Okay, and then in this, we also have, where's our KH? Here it is. In the theta component, we have a KH in there for our horizontal component, our horizontal acceleration. So using these two equations, where now we have the dynamic lateral earth pressure coefficient and our vertical acceleration coefficient and our horizontal acceleration coefficient, we can come up with the dynamic lateral force on our retaining wall. Now, a couple things to point out, and it's important for me to emphasize this. The variables here are different than the variables that I showed you in the earlier diagrams. Why in the world would I do that? Well, it's not my goal to confuse you. I'm just using the terminology and the variables that are consistent with the actual Mononabe papers, in case you go and choose to read them. And so, for example, beta. Beta for this, in these equations, is no longer the slope of the backfill behind the wall. This is the slope of the wall with respect to vertical. So what was theta in the earlier pictures is now beta in this equation. I is the slope of the ground behind the wall. So what is I in this equation used to be beta in the other equation. Everything else should be the same, except theta. Obviously, theta is not the slope of the retaining wall. That's now beta in this equation. So pay attention to that, and then you'll be fine. Okay, so for almost 50 years, the Mononabe-Okabe equation was used in engineering design. I'm going to call it the MO equation, just so I don't have to keep tripping over my tongue with the long names there. But in 1970, two of our geotechnical legends, the late Harry Seed and the late Whitman, co-published a paper where they identified two significant drawbacks of the Mononabe and Okabe equations. And these are those two drawbacks. Okay, the first one is how does an engineer select the horizontal acceleration coefficient, KH? This has been, this is a problem we identified in the previous lecture where we talked about seismic slope stability. Where do we get our KH from? Do we just use PGA, or do we use some fraction of the PGA? And so this is a big question, and a lot of people are still confused about this decades later. Most geotechnical engineers, even today, are going to use something between 0.5 to 0.8 of PGA for the KH in these Mononabe-Okabe equations, and that comes from various recommendations of different researchers. And most structural engineers, they get confused, and understandably so. They don't understand why we would use a fraction of the PGA at all. Why not just use the full PGA, 100% of the PGA? And so there's this constant frustration between geotechnical engineers and structural engineers that continues today. And it was going on back in the 1970s even, and beyond, or earlier than that. So that was the first problem. The second problem that Seed and Whitman began to point out is that if I start plugging in KH values that are greater than 0.4 times the value of gravity, MO equation, Mononabe-Okabe, begins to blow up and give me huge lateral pressures acting on my wall. And then if I try to put in values that are greater than 0.7 Gs, it completely blows up and gives me values that are astronomically large. And thus we have the problem. Because if I just do what the structural engineers are asking and say, why not just use 100% PGA, there's lots of places in this country where PGA gives me values of 0.7 or larger. And if I try to put those values into the Mononabe-Okabe and I compute those lateral earth pressures, it gets to the point where the lateral pressures are multiple times larger than the vertical stresses from that object. In other words, retaining walls would be leaping out of the sides of the slopes, and houses would be leaping sideways, that if this theory held true. And the thing that Seed and Whitman pointed out was Mononabe-Okabe never tested at values this high. This is all extrapolation, folks. If you guys are plugging in values into Mononabe-Okabe in excess of 0.4 Gs, you are extrapolating. Yet we've done it, and we've done it for decades. And so many structures have been over-designed because they've been designed for these methods. So Seed and Whitman proposed some changes. What they recommended was that if we're dealing with the active condition, which is a very common condition for retaining walls, probably the most common actually, they recommended first we're going to separate the earth pressure coefficients. So we're going to separate them into two components. This KAE that we're used to in Mononabe-Okabe is really the summation of the static earth pressure coefficient from the Coulomb method plus what they call the dynamic component, this delta KAE. Okay, so that comes just from the shaking itself. So if we add those together, we get what Mononabe and Okabe called KAE. So the question is, how do we get this dynamic component? Well, they recommended from all the studies they did that very simply you can closely approximate it by just taking it as 0.75 times kH, which if you want to use what the structural engineering community has been begging the geotechnical community for decades, and just say kH equals 1 times the PGA, then essentially that equation becomes 0.75 times PGA. So they say go ahead and use 0.75 times the PGA for that delta KE component. And it was easy. It was like, it blew everyone's mind how easy this was. But here's where things got really tricky, was the second thing they recommended. They said, now that resultant force, the resultant force from the static component, go ahead and apply that at its regular place of 1/3 up the wall. But this dynamic component, yeah, that one is more at a place they hypothesized was about 0.6 up the wall. And we engineers over time have said 0.6, that's too hard to remember. Let's just go ahead and call that 0.67 or 2/3 up the height of the wall. And if we do that, then that's easy to remember. So that led to what a lot of people started referring to as the inverted triangle. The inverted triangle is, let's go ahead and give us a clean slate here. The inverted triangle looks something like this, where if I have level ground and I have a retaining wall and I have some slope, and I wanted to draw the pressure distribution behind this wall, of course I have the static lateral earth pressure that it looks like the regular triangle. But now we have this inverted triangle that looks something like this. And this is from the dynamic component. This is, again, according to the theory of Seed and Whitman. So the whole goal is to add these two forces together to get my equivalent force acting on the wall and its equivalent location where those forces are acting on the wall. So all of this came from Seed and Whitman's, going back to some of the original test results from Matsuo from the 1940s, more than a decade after his original testing with Mononabe. Okay, so what's the problem? This seems great, right? But no, this is where geotechnical engineering becomes a soap opera, because engineers were so accustomed to the Mononabe-Okabe equation that when this Seed and Whitman paper came out in the 70s and these recommendations, engineers were more confused than ever on how to select their KH. Is KH 1 times PGA, or is it some fraction times the PGA? And they were confused on which active force method they were going to use. Were they going to use Mononabe and Okabe like they've been doing for decades, or were they going to switch now to these new recommendations from Seed and Whitman? A lot of engineers reported being uncomfortable with the Seed and Whitman recommendations because it just looked less conservative. They were drastically reducing the lateral earth pressures against structures, and they just, boy, that made them nervous. Anytime you lower those loads, lower those pressures, what if it fails? What if it fails? And so it made a lot of engineers nervous, and they didn't want to switch. So some engineers, really rogue engineers, started mixing and matching the techniques, coming up with their own techniques, cooked in their back labs and their consulting offices, and it became just the wild, wild west. And it was messy. And if that wasn't bad enough, some researchers started then introducing rigid walls. So these would be like basement walls. So everything we've been talking about are flexible walls in the active condition. But what if we have a rigid wall in the K0 at rest condition, which constitutes, most basement walls or walls against existing structures. So around the same time in 1973, a geotechnical legend by the name of Wood, he developed some early finite element models of soil. In his model, he fixed this soil to a rigid base. So the soil was attached at the base of the model, and it was confined by rigid walls, like a basement wall today. So when he ran these numerical models, his models showed these huge seismic lateral earth pressures on the rigid walls. So he published his results, and the engineering community blew up because they began to panic. Have we been under designing the forces on our basement walls? What do we do? And so they began in the 1970s designing for these huge seismic lateral earth pressures on these basement walls. But a lot of engineers, especially those that just looked at the data and said, this doesn't make sense. If these pressures were true, we'd be seeing basement wall failures all over the place in an earthquake. And we don't. We don't see them anywhere. And so they didn't buy it. They didn't believe it. So they went back and they started applying, again, the Mononabe-Okabe active force equations. These were the equations for flexible retaining walls in the active condition. Started applying them to their at-rest basement walls. So my question to you is do you think this is appropriate? And the short answer is no. No, it's not. It's not appropriate at all, but they didn't have anything else. And folks, this was the state of geotechnical engineering practice for decades. But in the late 1990s, a great researcher who's a friend of mine, Dr. Nick Sitar at University of California at Berkeley, decided to tackle this problem. And he took the lead in performing a lot of modern research in scaled physical models within a centrifuge, where he would instrument then these models of these walls and spin them, and then apply an earthquake motion in these models and measure the force in the models and then scale them up to the prototype scale. And he and his students evaluated both flexible and rigid retaining systems. So these would be active and at-rest earth pressures. So they've been looking at different types of walls. They've been looking at cantilever retaining walls, so that would be a case of a flexible wall. They were also looking at U-walls without struts, so again, a flexible wall. And then they were looking at U-walls with struts, so this would be a rigid retaining wall. So I was really pleased to get to listen to Dr. Sitar give a keynote address in 2012 where he reported his preliminary results and findings from all of this research. And his work has since been published in the ASCE Journal of Geotechnical and Geoenvironmental Engineering, where you guys can search it and find it. They have several papers published on each of these various tests. But what I want to do is summarize for you what Dr. Sitar summarized for me. So here we go. Here's what they found. First of all, they observed that nearly every documented retaining wall failure ever, whether it's static or dynamic, involved a couple of things. Either sloping backfill, waterfront, or other poor draining retaining structures, so water, and or soil liquefaction. If a retaining wall didn't have one or more of these three things, there's never been a documented failure according to or using modern engineering standards. Another thing that he observed is that many of the ancient and historic gravity retaining walls found throughout Europe and Asia, they've survived centuries and in some cases even millennia without being designed to our modern seismic standards. And if all the things that we've been believing from some of these researchers like Wood were true, those walls would be popping out of the ground millennia ago. And then third, and to me this speaks very loudly and speaks volumes, no basement wall constructed with modern seismic standards has ever been known to fail due to lateral earth pressures in an earthquake. They failed for other reasons: poor construction, structural flaws in the design, soil liquefaction, those kinds of things. But there's never been a wall identified to fail, or a basement wall identified to fail just from lateral earth pressures in an earthquake. And the fact that we've never had a documented failure suggests that maybe, just maybe, we've been over-designing for decades. So here are the recommendations from Dr. Sitar and his students for flexible walls. If you have a KH value less than 0.4 Gs, it doesn't matter whether you use the original Mononabe-Okabe equation or the Seed and Whitman simplified procedure. You're going to get about the same answer, generally within 5% of one another. So if your KH is less than 0.4 G, go for it. You can use either method you want and you'll arrive at the same place. Second, he said, if your KH is greater than 0.4 G, then he said the Mononabe and Okabe equations are going to give you very large lateral earth pressures. So if you are allowed to, in other words, if your specifications or the code that you're using or the owner who you're working for allows you to, use the Seed and Whitman procedure instead. Don't use Mononabe-Okabe. However, if you're forced to use Mononabe-Okabe, then you need to do whatever you can to get this KH down below 0.4 G. So try to justify a reduction in KH. A great example of this is from the work of Dr. Marshall Liu, who's a notable engineering practitioner in California. I'll show you a table here later in the lesson of recommended KH values from his research. Okay. The third recommendation from Sitar for flexible retaining walls is get rid of this inverted triangle. It's not real. It was a misinterpretation of Matsuo's data that Seed and Whitman made that resulted in this inverted triangle recommendation. Instead, let's go back to applying both the static and the dynamic components at the location of 1/3 up the height of the wall. So that really simplifies things. We don't have to worry about this inverted triangle anymore. For rigid walls, here's what Sitar and his students recommended. Get rid of the Wood 1973 recommendations. He said they're way too conservative and they do not represent true soil conditions and what has been observed in the field over decades. So just don't use Wood 1973 anymore. If you have basement walls that are less than 12 feet in height, and if the wall was designed for at least a factor of safety of 1.5 or greater for the at-rest static lateral earth pressures, or K0, then you don't need to worry about seismic earth pressures. You don't even need to include them in the analysis. In other words, this factor of safety of 1.5 will more than account for anything the dynamic component can add to your wall. He also said this, which I thought was interesting. Number 3, he said, if your PGA is less than 0.4 Gs, he said, and you have a rigid basement wall, then you don't even need to worry about the seismic increment. The dynamic component on that rigid wall will not be large enough to cause any sort of deformation or damage. However, if your PGA is greater than 0.4 G, and if your basement wall is higher than 12 feet in height, or 12 feet below the ground surface, then he recommends the Seed and the Whitman procedure for active loads can be used as a conservative upper bound estimate of the seismic earth pressures. Don't use Mononabe-Okabe. Use Seed and Whitman. Don't use the inverted triangle, but apply both the static and the dynamic loads at a height of 1/3 up the height of the base of the wall. So I referenced this table before, but I'm showing it here. Again, if you are being forced to use Mononabe-Okabe for your basement walls, and your earth pressures are larger than 0.4 Gs, then go ahead and try to again justify a reduction in your KH values. So here's a table from Liu and others in 2010 where it's based on measured forces on retaining systems. And so you can see this is the recommended KH values for different levels of peak ground accelerations from an earthquake. And then finally, he says, never apply the dynamic component from the Mononabe-Okabe equation or the Seed and Whitman method to the at-rest pressures. This is way too conservative. You want to, even though the basement wall is an at-rest condition, if you're going to account for the dynamic component of the earthquake, then go ahead and just use the active pressures with the dynamic component, and that will be fine. And even though it is at rest, not active, go ahead and just make that assumption and you'll be okay. So that's all that I have for you today, folks. I hope you enjoy the lesson and I hope you learned something. If you have any questions, let me know, and I'll be happy to respond the best that I can. Thanks for your attention and have a wonderful day.